Pre-calculus 5.1 day 1 notes. And so we have a group of trig identities that we're going to use to help simplify expressions. And so some of these you should already know, the reciprocal identities we have gone through. Sine is the same as 1 over cosecant. Cosine's 1 over secant, tangent's 1 over cotangent, and the others are true. And so now they just have u instead of theta as the angle, and so it's just another variable that we can use. Then it is going to be important that you know tangent is sine over cosine, while cotangent is the reciprocal, cosine over sine. And then we have these Pythagorean identities. And so we're going to be working with those as well. Before I get to looking at some of those, I want to talk a little bit about some notation that you need to be familiar with. And so if you have sine and theta is in parentheses, that's the same as sine of theta, or in this case, sine of u equals sine u. They are the same. If you have the product, say sine, and you can have different variables. So say this is the Greek letter alphabet alpha, sine alpha, cosine alpha. This means you're multiplying those. You will see those just written sine alpha, cosine alpha, and it means you're taking their product. Then we have, if we have a power, so say we have sine theta to the nth, we are going to write that sine to the nth theta, and those are going to mean the same. So if I have sine theta squared, that's going to be sine squared theta, and those mean the same. Now, I want to take a moment with this Pythagorean identity. Sine squared plus cosine squared equals 1. So we have sine squared, and I'm going to write theta plus cosine squared theta equals 1. And it's related to the whole a squared plus b squared equals c squared. That's why it's called Pythagorean identity, but it's sine squared plus cosine squared equals 1. You're going to need to recognize these in different forms. For example, if I solve this for cosine squared theta, that means I'm going to move the sine squared to the other side, and cosine squared is 1 minus sine squared theta. I can do the same thing, but instead solve for sine squared. So if I take this original one and solve for sine squared, that means I'm moving cosine squared to the other side, and I get 1 minus cosine squared theta. We are going to, at some point, take cosine squared theta, replace it with 1 minus sine squared. We're at some point going to take sine squared theta and replace it with 1 minus cosine squared theta. So we could even replace 1 with sine squared plus cosine squared. These are identities, meaning I can, if they're equal, I can replace one side with the other side. And so then we can do the same kind of thing with these other two Pythagorean identities. I want to take a moment, though, and talk about where do these come from? And to get this, 1 plus tangent squared theta equaling secant squared, or 1 plus tangent squared u plus secant squared u. What I'm going to do is I am going to take the Pythagorean identity sine squared plus cosine squared theta equaling 1, and I am going to divide both sides by sine squared theta. And when I do that on the left, and this is part of what you're going to be doing in your homework, is doing some algebraic things to different equations and expressions. I can divide, this means I'm dividing each of these by sine squared, and 1 over sine squared is cosecant squared theta. because the reciprocal of sine is cosecant. And so I get 1 plus, and then cosine over sine, if I go back up here, cosine over sine is cotangent. And so cosine over sine is going to be, oops, cotangent squared. And I'm getting this 1 plus cotangent squared is cosecant squared. So actually, I guess I got this one first. Similarly, and I'm going to do it right here, is if I start with sine squared theta plus cosine squared theta equals 1, but I divide both sides by cosine squared theta, I have sine squared theta over cosine squared theta plus cosine squared over cosine squared theta, and 1 over cosine is secant, so I get secant squared theta. And then sine over cosine, sine over cosine is tangent. So sine squared over cosine squared is tangent squared theta, plus then that's 1 equals secant squared. Or if I switch, I get 1 plus tangent squared theta is secant squared theta. So that's this one. So you can take the Pythagorean sine squared plus cosine squared equaling 1, divide by sine squared, and you get 1 plus cotangent squared theta equals cosecant squared. Or you can divide by cosine squared, and you get 1 plus tangent squared equals secant squared theta. So you can actually develop the other two Pythagorean identities from those. So we're going to see using all these identities in this chart as we simplify expressions or verify some equations are true. All right, so I'm going to go here, and I'm just going to kind of get rid of some of these markings because I'm going to be referring back to some of those. All right, so sometimes Pythagorean identities are in radical form, such as sine u is plus or minus 1 minus cosine squared u, or tangent of u is plus or minus the square root of secant squared u minus 1. And that is basically taking this identity solving for sine u, and when you take the square root, you get plus or minus, or taking this one solving for tangent, and when you take the square root, you get plus or minus. So they are rearrangements of those two. And the sign will the plus or minus will depend on the choice of u, of this u right here, and what quadrant that's in. All right. Okay, so this first example, the first few problems in your homework really are related to some things we've already done before. But I know that this has been a little bit of a struggle because to start with, when they give you both of these things, they're saying secant of x is negative and tangent of x is positive. By saying that secant's -3, we're looking at the sign, and sine is negative, and that combination tells us what quadrant we're in. It can only be one quadrant. And so you have to think on the quadrants. Where is secant negative? And secant is the reciprocal of cosine, so it's that 1 over x. So it's going to be negative where x is negative, which is either quadrant 2 or quadrant 3. Cosine's negative in quadrant 2 and 3. Secant is negative in quadrant 2 and 3. But if you combine that with the fact and tangent has to be positive, tangent's not positive in quadrant 2, but tangent is in quadrant 3, so it's not going to be quadrant 3 or 2, it's going to be quadrant 3 because that is the one quadrant where secant is negative and tangent is positive. So then I am going to go secant of x is negative 3. That means cosine of x is negative 1/3. And because it has to be quadrant 3, I am going to draw a triangle in quadrant 3 where this is my angle, and I guess I should really let that be x because that's what we have there. And cosine is going to be adjacent over hypotenuse. So negative 1 will be the x and the hypotenuse will be 3. And so then you are going to find the y value by going y squared plus a negative 1 squared equals 3 squared. Or y squared is 9 minus 1, which is 8. But because it's in quadrant 3, it's going to be a negative 2 root 2 when you take the square root and you simplify it. So this side is going to be negative 2 root 2. And so now we can find all 6 trig functions. So we've got secant, we have cosine. How if we do sine of x? Sine, using this as our reference angle, is opposite over hypotenuse. And then if I do cosecant of x, cosecant is the reciprocal of sine. So it's negative 3 over 2 root 2, but we are going to rationalize by multiplying by root 2 over root 2. And the cosecant of x is going to be a negative 3 root 2 all over 2 times root 2 times root 2 is 2. Excuse me, 4. Sorry. It's 2 times 2, which is 4. So there's the cosecant. So we have cosine, we already had secant. So now we need to figure out what is the tangent of x. Tangent is opposite over adjacent. So that would be negative 2 root 2 over negative 1, which means tangent is a positive 2 root 2. And then cotangent's the reciprocal of tangent, or it is adjacent over opposite, and rationalize. And cotangent of x comes out to a positive root 2 over 4. Positive root 2 over 4. So the big thing is figuring out what quadrant you're in, knowing that secant's negative and tangent's positive. Then you need to set up a triangle and use Pythagorean's theorem to find the third side. And this is the method I want to see. I want to see the triangle drawn. I want to see that you use Pythagorean's theorem to find the missing side and then find all of those. All right, so now we're going to go to simplifying. And when we are simplifying, we are going to try to rewrite with the least number of terms when possible. And one of the techniques that we're going to see in part A is change everything to being in terms of sine and cosine. Change things into being in terms of sine and cosine. That is a technique that works. We're going to simplify this. So now we're going to go back to those identities And cosine already is in terms of sine, but what about tangent? What was tangent? When we go back here, tangent is sine over cosine. So I'm going to use and replace tangent with sine over cosine and see what happens. And so you need to write the original down, work down the page, and then use the argument, whatever variable it is for the angles. Tangent is sine of that same angle, which happens to be alpha, over cosine of that alpha. And then we're taking that times cosine of alpha, and that is, we can think of as over 1. And so with fractions, when you're multiplying, that numerator can cancel out that denominator, and you get sine alpha over 1, which is just sine alpha. And there you have simplified that. Now, in part B, we're going to need to see this as two terms, but the two terms both have this secant x in it, meaning they have a common factor. And again, this is kind of new, so you're gonna have to practice this a little bit. And so I'm going to, just to show, I'm going to let secant just be s, and then I'm going to think of sine as w squared. I can't use s for it because I'm already using it for secant. So I can kind of think of this as s minus s w squared. I'm just doing this so that you can kind of get a feeling for this with it being a little less abstract. If I gave you s minus sw squared and I asked you to factor it, I hope that you would write it as s times 1 minus w squared. So you're taking out the s. But now you're going to need to do this in terms of secant. So what that means is I can take out, so put my equals, I can take out a secant of x. Don't forget your angle. Call that the argument. You need this x right here. So I'm going to pull that out, and when I pull it out, I get 1 minus sine squared x, because I pulled out that common factor from both of them. Now this is where you need to know your identities, so you're going to have to get very familiar with them, where when I see 1 minus sine squared x, I remember, oh, we had sine squared u plus cosine squared u equals 1. And if I solve that for cosine squared is 1 minus sine squared u. I showed that back here, right there. It's a rearrangement of this sine squared plus cosine squared equals 1. And so I have this 1 minus sine squared. I can write it with fewer terms by replacing it with cosine squared. So I'm going to write this cosine squared x. And then I'm going to apply, sometimes it's nice to change things in terms of sine and cosine, and secant happens to be 1 over cosine. And I can think of the cosine squared x as being over 1. And so then I've got this can be 1 over cosine x times cosine x over 1. Cosine squared just means you're taking it times itself twice, and one of those cancels with one of those. Or I'm going to say this cosine takes out the square, and that whole thing simplifies to cosine of x. So there's some algebra things that you need to be aware of and work on to be able to do these accurately. Then we have factoring trig expressions. And when we say factoring, you're going to end up writing it as a product of one or more terms. And so in part A, I see sine squared minus cosine squared. And I am going to think of this as s squared for a moment minus c squared. I don't want it all done quite like that, but to get to see it, it's sometimes easier to, let's simplify these expressions. We've got a sine squared minus a cosine squared. Well, we have this, if you have a squared minus b squared, it factors a plus b, a minus b. It's something, it's a difference of squares factors a plus b, a minus b. Well, that's what we're going to end up doing with the s squared minus c squared. We're going to have an s plus c times an s minus c. But we have to remember, wait, it wasn't just s's and c's, it is sine squared and cosine squared. So this factors sine of x plus cosine x times sine x minus cosine x. So what we've done with variables, we're doing with trig expressions. And that is writing it as a product. It's factoring it. So on this next one, it's quadratic in nature. You have a cosecant squared, a cosecant, and then just a constant. And so if I just for a moment, think of this as cosecant, let this be a c squared, and let this be a c. Think about this 3c squared plus 2c minus 8. Or I could be thinking of it as 3x squared plus 2x minus 8. I want to factor this. And to factor this, to get a 3c, I need a 3c and a c. And then I need things that multiply to be a negative 8. But then when I do the outer and inner product, I get a plus 2c in the middle. So if I tried plus 2 and minus 4, this would be a minus 12c and a 2c. That's a negative 10c. That didn't work. So that's not going to work. What if I switched them and made this a minus 4 and this a plus 2? That's going to work because this is 6c and this is a minus 4c, which add up to 2c. So that's the correct factoring of that. And so now, though, I need to go to what this was originally. Make sure you always have that original problem. And instead of writing it with a c, I'm going to use cosecant. So I have 3 cosecant, don't forget the angle of x, minus 4, and cosecant x plus 2. And there you have factored. So it's related to how you factor quadratics. Only you're working a little more abstractly with these trig expressions. Example 4. So it says factor, but unlike in example 3, part B, they were both cosecants. Here we have a cotangent and a cosecant. I need to make these the same trig function so that I can get it to a quadratic form and I can factor it because they have the same trig function. And so I need to go back to that chart and look at the cotangent and cosecant and everything I have there and see what are my tools that I can use. Is there something that relates cotangent and cosecant? So I'm going to go back and I look at something that relates these, cotangent and cosecant. Well, I've got a cotangent squared, and this Pythagorean identity relates cotangent squared and cosecant squared. So I'm going to take that, which is 1 plus cotangent squared, and we've got theta here, so we'll use theta, equals, it was cosecant squared theta. One more time, right here, 1 plus cotangent squared equals cosecant squared, but our angle's theta instead of u. And I can then choose to solve this for cotangent squared, subtract 1, and then cotangent squared theta is equal to cosecant squared theta minus 1, meaning I can replace cotangent squared theta with this cosecant squared theta minus 1. And that's what I'm going to do. I am going to replace cotangent squared theta with cosecant squared theta minus 1. Then I still have a minus 2 cosecant theta minus 7. So I'm going to get this in the same trig function. I have cosecant squared theta minus 1 minus 2 cosecant theta minus 7. And on these, you need the theta on every step for every argument. Then I can combine the minus 1 and the minus 7. I have a cosecant squared theta minus 2 cosecant theta minus 8. So just off to the side, I can think of this as a c squared minus 2c minus 8. If it's feeling a little bit too much, I'm going to think of cosecant as c in this case. And I have it squared and then minus 2c minus 8. And think about if I was going to factor that, I would get a c minus 4 and a c plus 2. That would get me my minus 2c in the middle and a minus 8 at the end. But it isn't, c is replacing cosecant, so that means that this is going to factor to cosecant, don't forget the theta, minus 4, cosecant theta plus 2. So sometimes you have to replace things so you can get it into the same trig function so it's ready to be factored. And notice we've got some hints about what homework problems you might be using these techniques on. And then example 5, simplify this expression. Simplify this expression. And for this one, we're going to use just kind of a combination of some different things. And first of all, I see two terms that both have secant, meaning I can write the original problem, go down the page, not left to right, put an equal sign, and I can, that's just part of communicating, I can pull out that secant t. If I pull that out of each term, I am left with cosecant t minus sine t. So I just took each of these out, and that left that cosecant t minus sine t. Now what I'm going to do is change to sine and cosine t. And part of my thoughts is none of these are squared, so I can't do any replacing with the Pythagorean identities. The Pythagorean identities need things that are squared. I don't have anything squared. And one of the techniques is if you get them into sine and cosine, when you don't have squared terms, sometimes that can help. So secant is 1 over cosine t, and cosecant is 1 over sine t. And then I have minus sine t. And now what I'm going to do is I'm going to get a common denominator. I'm going to change this to a bracket. I'm going to get a common denominator here. And to do that, I'm going to think of this over 1, and I'm going to multiply the top and the bottom of that single fraction by sine t over sine t. And sine t times sine t is sine squared t. So in this next step, I have 1 over cosine t, and in here I have a 1 over sine t minus sine squared t over sine t. And I'm going to leave this 1 over cosine t on the outside. Now I have two fractions that have the same denominator, so I can write it all over sine t, and I have a 1 minus sine squared t. And this 1 minus sine squared t is going to be something that you're going to want to be very familiar with in terms of Pythagorean identities. 1 minus sine squared t, if I go back, one minus sine squared t is the same as cosine squared t. So here I have it in theta, but theta can have different variables. So in the problem we're working, it's a t for a variable. So 1 minus sine squared t is cosine squared t. So I can replace 1 minus sine squared t with cosine squared t. So I've got that cosine squared t is 1 minus sine squared t. So I have 1 over cosine t times cosine squared t over sine t. And we saw this a little bit earlier, that this cosine t can take out one of those, because this is really 1 over cosine t times cosine t over sine t. So one of those can take out one of those. And that leaves me with cosine t over sine t. But wait a minute, cosine over sine? It seems like there's something in that box that's cosine over sine. Let's go back. And sure enough, cosine over sine is cotangent, so we can write it as that single trig function, cotangent t. So cosine over sine is cotangent. And so we're going to go back here, and we're going to say this is cotangent t, and don't forget that argument. You have to be a little bit patient with these. You've got to really dig in. Do not use quick electronic ways of getting answers, because you've got to learn how to sort and be able to choose the correct if you're really going to learn this stuff. So, and use academic support to get help. Do your problems in advance and ask questions in class. You're going to need to do that. There you go.